So firstly, thank you everybody for joining this DEP's live webinar. Good morning, good afternoon, good evening, okay, to all the participants who were able to, join this meeting. Okay, so it's a pleasure meeting you all. So with that note, okay, I mean, we can start with our presentation. Okay, so as you know that today is, we are going to take a deep dive into our battery thermal runaway sensor. Okay, we are going to showcase our complete capabilities. This battery sensor, thermal runaway sensor. I mean, what are the advantages it has got? Okay, and so far, what are the technologies and development side? I mean, what we have achieved. Okay, so starting with that, I would like to flash a quick agenda for today's webinar. So introduction wise, myself, Sadaf, and I work as an account manager in Detroit Engineered Products. And how we had planned it, like, many of you who have joined this webinar, okay, might not be familiar with DEP as a company. So we will try to give a quick 5 minutes overview about DEP as a company background, I mean, how we position ourselves in the market and overall as a company background, okay, I mean, what we offer. And then my colleague who is also in this call, okay, Yusuf, who is going to, take the other round of the discussion, okay, and which could be very dedicated to the battery thermal runaway sensor, okay, and then later part of the session, we can reserve it 5-10 minutes, for any questions and answers. So in that case, I can get started from my end. So DEP stands for Detroit Engineered Products. We are a 27-year-old company now. We are headquartered in Troy, Michigan, okay, and we have other offices in India, China, Japan, Canada, Mexico, and Brazil. And in Europe, we work with our partners, okay, like France, Italy, Germany, Poland, Korea, and all. Okay, and whatever you see on the right hand side, these are the four divisions, I would say. I mean, I mean, as we speak, I mean, we are operating in all these four divisions. I'm going to cover, all these four divisions, one by one. So first is the engineering consulting. So here we support companies for any turnkey projects, ODC projects. Okay, it could be anything on the design side, virtual validation, CAE, anything on the lightweighting optimization. Okay, I mean, it doesn't matter. Okay, on the mechanical side, electronic side, electrical side. Okay, I mean, we can support that. Okay, in the software division, I mean, DP has got own CAE-based software, okay, which is called Meshwork. If you happen to know Hypermesh answer, okay, so it's a very similar software, Meshworks, okay, and I would say, I mean, it does, many more magic, okay, in terms of overall advantages, okay, as compared to the competitors in the market. And then we have product development. So here we support our companies end to end, to design the product. Okay, so we are going to touch base on this sensor product. Okay, I mean, from this particular division, and then talent acquisition. So here we support companies for any of the on-site contract resources. Okay, I mean, we can support our customers. Okay, so these are the four divisions we are operating as we speak today. So here, I just would like to quickly cover the complete product development ecosystem. Okay, so we can proud to say that we could be a one-stop service provider. Okay, so all the way starting from the benchmarking, we have our own lab at our Troy office. We have our own 3D scanner. Okay, through which we can scan the products. It doesn't matter how big the component is. We can scan the component and further we can convert the scan data to CAD model to FEA model for further benchmarking studies. And then design, here we support companies, for any type of concept design, product design, doing any type of 3D modeling, 2D drawings, layout drawings, schematic drawings. It doesn't matter, okay, like I said earlier, mechanical, electrical, electronics, we can support that. And CAE, CFD, we are very strong. Okay, so any type of virtual assessment, I mean, we have the right expertise, I mean, to support that. Okay, whether it could be on performance optimization, whether it could be on material optimization, whether it could be on thermal management. Okay, I mean, we could support that. And controls MBSC. So here we support the entire V cycle of the control systems, okay, all the way starting from the requirement gathering, doing all the system level architecture and the bottom level of COK where we do all the code generation, algorithm development, okay, and then the right side of the VOK where we do all the integration, hill, cell, mill testing, I mean, we can support that. Okay, so it could be okay. So that is the entire recycle, we can support. Okay, and on the manufacturing side, here we support for any type of flow simulation, mold flow simulation, stamping simulations, we can support it. And prototyping and testing, we have an ecosystem where we could support companies for low cost production for testing. Okay, we don't do it in house. Okay, but then we have an ecosystem supported. And electrification. Okay, so here also DP had invested up, past 15 years. Since a lot of automotive division is moving into electrification. Okay, so we had also invested a lot in this area. Okay, so I could say that pretty much every second or third EV company in North America, we are working for them. Okay, sometimes we support them on component level, sometime on subsystem level, or sometimes for the entire full vehicle level. Okay, so all the way from electric powertrain, motors, battery control systems, we can support it. And AIML, okay, this is getting very popular in the market. Okay, so we had developed our own AIML framework. Okay, so through which we are offering this advanced machine learning services also. Okay, so this is the overall, I would say the complete 9 yards of product development life cycle, how we are supporting our customers. And secondly, I would like to highlight here, okay, this is a very comprehensive chart, I would say, okay, talking about, commodity by commodity, bumper to bumper, okay, how, in terms of skill metrics, how we are supporting our customers, okay, yeah, majority of the customers are coming from the automotive domain, okay, since we are working with almost like, more than 300 plus customers. So here you can see, okay, the left-hand side, these are all the functional areas all the way from benchmarking, doing all the designing work, doing all the systems engineering work, doing all the detailed design work, all the way doing all the CA assessment. Okay, whether it is FEA, CFD, crash, NVH impact. Okay, we can support it. Doing all the optimization, lightweighting, all the way from electrical controls. We can support it. Okay, and the top row. Okay, these are the subsystems. We can support. Okay, so these are pretty comprehensive chart. Okay, as you can see, full vehicle, BIW closures, bumpers, suspensions, interior seats, battery pack, okay, transmission, we can support it. Okay, so this is a pretty, I would say, comprehensive chart how we are supporting our customers. Okay, all the way from OEM, Tier 1 suppliers, globally. So software development I already spoke about. Here we have our own CAE pre-processor software, okay, which is called Meshworks. Okay, so here we here we also sell our software, okay, to our customers. And second is the product development. Here we support our customers end to end, for designing the product. So whatever the images you see on the screen, these are some of the end to end development projects that we had, that we had initiated in house. Okay, we had not mass produced these products, okay, because we are not the manufacturer, but to showcase as a technology demonstrated to the customer that DEP has got the end to end capabilities. We had successfully delivered these projects. Okay, so like I said, as a technology demonstrator, so for India market, we had designed and developed a complete electric two-wheeler scooter. Then we have electric this power tool, and in partnership with Aramco, we had designed and developed this single-cylinder engine. Then we have combustion sensor. Then we have drone. Okay, so pretty much, okay, as you can say, we can support end to end for the complete product development cycle. And then on the talent acquisition, okay, so here we support all the companies for short-term, long-term, any resource support you might require on-site, okay, on the contract opportunities, okay, we can support you, okay. Whether it doesn't matter, it could be electrical engineer, powertrain engineer, controls engineer, battery engineer, CA engineer, crash engineer, CFD engineer, we can support it. Okay, we have a very good pool of resources. Okay, since we are working with a lot of OEMs, Tier 1 suppliers. Okay, we have got a couple of vendorship from all these companies. Okay, so we can support you with any type of short-term, long-term needs you might have on the contract side. Coming to our global reach, okay, so overall we have 800 plus employees. In North America, we have 100 employees, and our majority of the strength is in India. India, we have three locations: Chennai, Bangalore, and Pune. We have almost like 680 employees. So pretty much whatever you see, all the red phones, these are all our our own offices, okay, and blue phones, here we work with our partners. And in terms of industry wise, okay, 80-90% of the revenue of DEP is coming from the automotive division, but we also support other industry verticals like biomedical, consumer electronics, aerospace, defense, and all. Okay, we do support other divisions also. Okay, so this talks about the global strength of DEP, what we have. And coming to the next slide, okay, I mean, I mean, here you can see the partial list of our all the customers. Okay, so geography-wise, you can see all the pretty big names. Okay, from OEM Tier 1 suppliers, how we are supporting North America, Europe, Asia, and all. Okay, so sometimes we support them on services-based engagements. Okay, for turnkey projects or probably like setting up some ODC team for them. Okay, having hybrid kind of approach, like I mean, local presence in US, having some coordinator, and then heavy lifting could be done in India office. Okay, and then sometimes we support them, sometimes we sell our software to them, or sometimes pure play, on the staffing contract opportunities, we support them. And secondly, on the ISO certification side, we are, I mean, everything is in place. I mean, we are ISO 9001 certified and all. Okay, so pretty much you can have the peace of mind that whatever the work we are going to deliver it for you, it is going to meet the quality requirement. Okay, and we are also a minority business enterprise. Okay, we are a woman-owned company. Okay, so sometimes the companies do get some subsidies or benefit, working with us. Coming to the next slide, I just thought, okay, probably since we're talking about the company overview, okay, maybe I could also highlight one testimonial. The reason is I am specifically highlighting this testimonial because this particular gentleman, is a known name in the automotive domain in the Detroit area. And back then in 2015-16 time frame, we did one vehicle lightweighting project. Okay, so he was ex Stellantis. Okay, I mean, chief of body structures and all. Okay, so he was very pleased how we had supported them. Okay, so he came forward on social media platform like LinkedIn and all, and then appreciated DEP, like the kind of work we had done. Okay, so currently he's serving managing director at GD Power. I thought probably like I mean, we have many more testimonials, but I thought since interest of time, I could flash this testimonial for everybody's reference. Now, before I hand it over to for our technical topic, okay, I just would like to highlight like as a company how we are organized. Okay, so we have a pretty structured team. I mean, just moments back, I highlighted, I mean. This component by component, how we are supporting our customer. So here, I mean, in design engineering, we have 100 plus resources. These are our all in-house resources. So as you can see, one team is doing all the benchmarking. Okay, one team is doing all the BIW closures. One team is doing all the chassis, exterior, interior, powertrain, and one team is doing all the advanced manufacturing, costing, tooling, shoot cost analysis, and all. Okay, so this is the design team. Okay, similarly, we have a vehicle CA team. Okay, so vehicle CA team pretty structured. Okay, I mean, we have CA model building team who does all the meshing and all. Okay, model building, crash safety. Okay, all these they do. Then NVS durability, MPD analysis, CFD thermal methods automation, lightweighting optimization. Okay, this is one of the core area. Okay, where DEP has been I mean known in Detroit area. Okay, doing a lot of lightweighting and optimization projects. Okay, both for vehicle side and powertrain side. And like that, we also have a powertrain team. We have 90 plus resources, all the way from durability, NVH, CFD thermal, system dynamics, methods development, lightweighting, optimization. And we also have a very organized team on the embedded side. Okay, so we have 60 plus resources, entire V cycle, we are supporting. Okay, so doing all the requirement gathering, all the way doing system level modeling and all. And one team is doing all the code generation, algorithm developments and all, and the right side of the V and all. Okay. Okay, so with that said, I would end my company overview here, and I would request my colleague, okay, Yusuf, to take it forward, okay, from here to start with the battery thermal runaway presentation.
So, welcome everybody to the webinar. My name is Yusuf Mansour. I'm the mechanical engineer at DP. I've been working here for about 5 years. And this time, we've been working to develop our spark plug and glow plug sensors and the project lead for the development of this thermal runaway sensor. So today we're going to go through two topics. One is understanding thermal runaway, where we'll touch into the triggers, the battery safety stages of thermal runaway, the battery cell mechanism. And then we're going to go into introducing our technology. So I'll show the sensor, the validation, performance, and some takeaways. So starting with thermal, understanding thermal runaway. So by definition, thermal runaway is the propagating exothermic reaction that a battery undergoes, leading to dangerous situations if not mitigated properly. So I've here listed a number of triggers to thermal runaway. So you can see here there's the temperature increase, physical damage, you have overcharging, you have manufacturing impurities, and you have excessive usage. Now, an increase in thermal in temperature can be due to atmospheric conditions or can result from other triggers. So this can increase. This increase in temperature can melt the separator between the anode and cathode, and it can create an internal short circuit. Physical damage, on the other hand, can be due to punctures or deformations, typically from vehicle crashes, and this can result in the battery short circuiting and internally and externally. So, overcharging and excessive usage can heat the battery, resulting in an internal short circuit, the same way that a temperature increase trigger does. And manufacturing flaw is a rare scenario, but it is possible, where it can cause an internal short circuits in the battery even during normal operations. This can be due to many things, including debris or impurities in the battery. Now, all of these internal short circuits ramp up the temperature even more and propagate to other cells, causing thermal runaway. Uh, Thermal runaway can also lead to safety issues. So, failure to safely mitigate thermal runaway can result in the battery producing toxic gas and other harmful chemicals into the atmosphere. So, any bystanders or passengers in the vicinity can inhale these hazardous gases, causing harm to that individual. So, these same toxic gases are flammable, and heat generated from the thermal runaway can cause the battery's electrolyte to combust or explode, resulting in fire and debris to project outward. Again, this makes it unsafe for bystanders and passengers. The pressure buildup and combustion from the thermal runaway can cause structural damage to the battery housing, as well as the vehicle or structure itself. This results in more wasteful material and renders it difficult to recycle. So, to ensure battery safety is properly maintained, there are three key components: correct adherence to the battery regulations, early detection of thermal runaway, and continuous monitoring with the BMS to take the proper protocols once thermal runaway is detected. Now, the regulations currently in place are the GB 38031 2020 and the UN ECE R100. Both this is in for the Europe and China. Now, these state that the thermal runaway warning must give an alert 5 minutes prior to any hazardous conditions due to the thermal propagation. And effective next year in July, the GB 38031 regulation will include no fire and no explosions from the battery before or during the thermal runaway. So this makes things difficult, but not impossible, as there are stages before the thermal runaway where detection can be made. So all of these stages in green, you can prevent the thermal runaway, while after this certain points, thermal runaway can be prevented. So these stages I've got from a article. Now it states here that the first step is the metal ion dissolution. This is where heat breaks the crystal structure of the cathode, resulting in the migration of metal ions into the electrolyte. Now, in the solid electrolyte film decomposition, this releases more heat, resulting in more metal ion dissolution. You have the reaction between the lithium and the electrolyte, again releases more heat, and it causes a chain reaction of degradation processes. At the next step, you have the separator melting, and this results in micro internal short circuits, again resulting in temperature increase. So then the gas starts to build up at this stage here, uh, and it starts to increase in pressure from the gas formation. And then that's when the safety vent completely breaks off. And then you have here the separator melts completely at this point, and this causes a large scale internal short circuit. Now, the short circuit leads to the decomposition of the cathode and the electrolytes. Um, the decomposition of the cathode ends up resulting in a release of oxygen, which reacts with the electrolyte and can result in combustion. You have the decomposition of the electrolyte, which begins and it releases gases. And at this point, the anode can react with the binder material, increasing the temperature more. And at this last stage is where combustion can occur from the ignition of the gases. So this here is a mechanism of battery cell failure step by step. So we start healthy. During formation, the electrolyte reacts with graphite and builds a protective layer called the SEI. This gives off a little ethylene plus tiny amounts of hydrogen and carbon monoxide, then settles down. Under fast charging or in the cold, the lithium can plate onto the anode and grow dendrites. The plated lithium reacts with the solvent and makes more hydrogen and light hydrocarbons. As the cell heats or ages, parts of the SEI and the solvent break down, adding carbon dioxide, carbon monoxide, and more ethylene. If dendrites pierce the separator, you get an internal short, joule heating spikes, and gas generation jumps. The safety vent then opens and hot electrolyte vapor is expelled. Meanwhile, the cathode starts releasing oxygen, which chemically burns the solvent and pushes the system towards thermal runaway. So, free electrons, hydrogens, lithium ions, these are all released before thermal runaway prior to the onset of deterioration due to thermal propagation. The lithium metal and lithium ion particles, which are referred to in literature as dust, contain an organic electrolyte that decomposes during thermal runaway. This organic electrolyte is comprised of a lithium salt dissolved in an organic solvent. Ethylene carbonates, diethyl carbonates, dimethyl carbonates, and the rest of this list are potential organic solvents in this electrolyte. This wide range of organic solvents can result in variations in the concentrations of venting gas constituents, regardless of the battery chemistry. Now, our sensor detects these ions and these particulates that this battery emits. So that concludes our first topic. Now we're going to go into the topic of our sensor, which detects the ions and particulates mentioned in the previous slide. So this here is our sensor. You can see on the right side this small black module, and this is what we place on a battery cell. And on the bottom, this is where we place on the module or pack level. So our sensor size and shape can be changed due to customer specifications. You can see it can be as small as a dime, or it can be as small as a dime with an external signal conditioning unit, or it can be all wrapped up in one package, similar to the size of a credit card. And this can be placed at the module or pack level. Now, this sensor detects the free electrons and the ions from the battery, and it can be placed at the vents or in the ducts or within the modules, or it can wherever it can get access to those floating electrons. Now, the vent holes that you can see here allow for the free flow of the ions for the detection. The sensing and the conditioning units are located inside the casing of this sensor, with a connector here to the for the power into the sensor, as well as the sensor signal out to the battery. Now, this is all for the module pack level. For the cell level, we integrate this into the cell into the battery cell, where it has access to the chemistry occurring inside the battery, and this is connected in line to a signal conditioning unit, which is going to be on the module level or pack level, connected to all the sensors on these cells. So we've conducted a number of tests to validate the detection of our sensor. So the three I'm about to show you were done with a 24 amp hour NMC combination blend cell. So in this test, we had 4 cells placed side by side, as you can see here, on these 3 numbered cells, with a sensor shown in green here on top of them. And a heating element, you can see this red line here, was attached to cell number 1. This blank cell, we did not have a sensor connected to it. It was just another cell in the line with this combination. Now, you have the plots on the right here, and they're aligned by minutes on the x-axis. You have the voltages on the y-axis here on the left, and on the y-axis on the right, you have the temperature in degrees Celsius. So each of these show the detection of the sensor in green for each cell, with the plots of the thermocouple placed on each battery in coordinate with its color. So you have orange here for cell number 1, cell number 2 is yellow, and cell number 3 is blue. So you can see from the top plots, the detection for cell number 1 triggered about 7 minutes after 7 minutes after the start of the test. And it reached around 70 degrees Celsius where it started detection. 2 minutes after that, it reached its maximum point of detection, stating that the deterioration of the cell has rapidly increased. Then we have, meanwhile, in cell number 2, it was being heated by proximity and not directly, as cell number 1 was. And it took about 11 minutes for it to detect, and about 1 minute for the sensor to state that it's rapidly increasing the deterioration. Now, about 2 minutes after that, you can see that it went into thermal runaway. Cell number 1 goes into thermal runaway first. Followed by that, you have cell number 2, and this trigger causes a domino effect in which cell number 2 went in way. Then you have cell number 3 caught flames. This blank cell caught flames, and then cell number 3 immediately after that. So you'll notice that there was no deterioration detected in cell 3 because there was no heating to it until the first cell started catching flames, and the flames propagated from cell to cell until it pushed cell number 3 into thermal runaway. So this test here shows a basic overcharge test. You have the x-axis here in time, in minutes. You have the y-axis on the top plot is the temperature in degrees Celsius. And you have the y-axis on the bottom plot here on the left is the battery voltage, while on the right is the sensor voltage. So this green line is our sensor signal. This red line is our battery voltage. And these 3 colored lines, it's blue, orange, and gray are the thermocouples placed around the battery at the positive terminal, negative terminal, and the side wall. So you'll see here that we were charging at about zero point 0.5 C, and for about 23 and a half minutes, the sensor triggered and detected the deterioration. About a minute after that, we noted that it rapidly increased in deterioration. And about 3.5 minutes after that, the cell underwent thermal runaway. So, all in all, this took about 5 minutes of detection prior to thermal runaway, charging at half C. Now, this last test I'm going to show you, we repeated the same overcharge, but with a different approach. In this case, what we did was we charged it until the sensor detected its massive increase, so rapidly increasing the deterioration. And at that point, we cut the charging of the cell. And we did it again once more, and then again at the end. So here, the plots are aligned the same. You have the temperature on the top graph aligned with the x-axis in minutes, voltage for both the sensor and the battery on the y-axis on the left here. Or sorry, this is the voltage for the battery, while the sensor voltage is located on the right. So this green is our sensor voltage, red is the battery, and you have the three thermocouples detecting the positive terminal, the negative terminal, and the sidewall temperatures, all in degrees Celsius. So starting from the beginning of this test, about 40 minutes in, we detected a rapid deterioration. So at this point, we stopped the overcharge, and the temperature of the cell at this point read about 75 degrees Celsius. And then after that, after it read 75 degrees Celsius, it slowly started decreasing until we started the charge again. But in that time that it was decreasing, our sensor, after it detected its max point, dropped down, realizing that deterioration isn't happening as much, it's reducing. But then it noticed another spike in deterioration a little bit later that it was detecting. The chemistry started changing again, even though temperature was high, but there was no charging happening. So we waited about 20 minutes after we stopped charging, and after the sensor detected that there was no deterioration occurring, we started the charge again. And at this point, the temperature gradually increased before, and our sensor kept going for about 20 minutes until it detected again another rapid increase in deterioration. At this point, the temperature was around 102 degrees, so we stopped charging again. You notice that the battery voltage dropped, and at this point, the temperature started slowly decreasing until it got to about 43 degrees Celsius or about 39 degrees Celsius. During that time, our sensor was detecting deterioration after we stopped charging. It dropped, the deterioration dropped and went back up again, dropped, and at a certain point, it noticed a steady rate of deterioration. The chemistry was changing constantly, and this kept going for about 20 minutes. At this point, you'll notice it's 43 degrees Celsius, and our sensor spiked up again in a rapid deterioration, noting that there is something going on with the battery. Regardless that the temperature dropped to 43 degrees, there was no charging happening on the battery, but it was detecting that there was more chemistry changes happening within that cell. So we waited for another 15 minutes before we were running out of time for our test. So we decided to start charging again. At this point, the once we started charging again, immediately after we pressed charge, the battery completely died. It went into thermal runaway. and caught flames. You'll see the spike in temperature happened right after. At this point, you'll notice this little drop here is actually what happened where our system malfunctioned when we tried to charge it because it couldn't detect anything, and it restarted itself. After it restarted, we pressed overcharge again, and this little spike is where it went into thermal runaway. So immediately after starting, so our sensor was able to detect that the uh, battery was deteriorating to a point where it is approaching its thermal runaway. So you can see here that we were actually able to delay that thermal runaway from happening for about an hour and a half from our first detection point here all the way till we pushed it into thermal runaway here. So this very big delay can actually be extended because obviously here we're doing a very aggressive test. This time delay can be extended and you can even discharge the battery to prevent it from going into that thermal runaway from the moment of our detection. So this all shows also that that independent from the temperature, we're able to detect early enough to mitigate and even prevent that thermal runaway from happening. So we know that thermal runaway is the propagating exothermic reaction resulting from a short circuit that deteriorates the battery and produces toxic flammable gas. So to ensure battery safety, we need to follow set battery safety regulations and have an early detection of thermal runaway and maintain proper continuous monitoring with the battery management system. Now, our sensor can provide these early warnings to thermal runaway by detecting those free electrons emitted prior to the battery deterioration. Since it detects those free electrons, the chemistry of the battery has no effect on the capability of our sensor. And finally, to ensure optimal integration of our sensor, the shape and size can be altered to the customer requirements. So, as our next steps, our main goal is to bring our technology to markets in different areas related to battery safety and integrate our technology with companies in different sectors, not only to the automotive sector like electric vehicles, but also to the aviation sector as well as uh, electric planes, electric bikes. We found demand in electric scooters as well, and even in the battery storage safety sector and battery recycling center, we found that there is a need for this kind of detection of thermal runaway. And this technology could also be used for battery pack testing for design and pre-production, where it can provide more information of the deterioration of the battery and the location where the thermal runaway starts. So thank you for listening. Please contact us for prototype evaluation, joint testing, or pilot projects.